Good morning to one and all. In today's class, we are going to prove some properties of continuous functions. Before going to prove the properties of continuous functions, we are going to define some definitions. Definition of bounded above. A function f of x is said to be bounded above in the set D subset of R if f of x is defined in the set D subset of R. Second point is there exists a real number capital M such that f of x is less than or equal to m for all x belongs to D. This definition I already explained to you. So in this situation we can say that f of x is bounded above and m is called upper bound of f of x. Now we are going to define least upper bound or supremum. So a real number m is said to be the least upper bound or supremum of the function f of x defined over closed interval a comma b. So once listen, a real number capital M is said to be least upper bound or supremum. Least upper bound or supremum of a function f of x defined over closed interval a comma b. That means this real number m is said to be least upper bound or supremum of f of x where x is any value between a and b and also x is equal to a or x equal to b. Closed interval means end points also including. If capital M is an upper bound of f of x, that means f of x is defined on closed interval a comma b. This is first point. Second point is f of x is less than or equal to capital M for all x belongs to closed interval a comma b. Whenever these two conditions are satisfied, then we are going to say m is an upper bound of f of x in closed interval a comma b. Second point, for all epsilon greater than 0, that means epsilon greater than 0 is a positive quantity. There exists a point x1 belongs to closed interval a comma b such that f of x1 is greater than m minus epsilon. Whenever this condition is true, then we say that the real number m is least upper bound or supremum. Once again, here m is called an upper bound. Whenever we know an upper bound of a function, if 5 is an upper bound of the function, then the numbers greater than 5 are also upper bounds of the function. Now this set is set of all upper bounds. Set of all upper bounds. In this upper bound set, we can easily find least one, that is called least upper bound or supremum. Whenever we fix one real number as least upper bound, then the number less than this least upper bound is not an upper bound. For example, if 5 is least upper bound, then 4 cannot be least upper bound. That means 4 cannot satisfy this condition. Here we have less than or equal. So, the number less than m is m minus epsilon. Whenever these two are false means less than false, equal false means greater than. Then m is called least upper bound. Once again, the second condition implies any real number smaller than m, that means m minus epsilon cannot be an upper bound of f of x. If upper bound means f of x value must be less than or equal to m minus epsilon, but cannot be means it is not less than, it is not equal. That means f of x1 is a point on closed interval a comma b, value is greater than m minus epsilon. The least upper bound of f of x is denoted by LUB. Next definition is bounded below. A function f of x is said to be bounded below in the set D subset of R if f of x is defined in the set D subset of R. That means the value of f of x is finite in the points of D. So, D contains some real numbers. At these real numbers, the value of f is finite. Then we can say that f of x is defined in the set D subset of capital R. Second condition is there exists a real number small m such that f of x is greater than or equal to m. Then this real number is called lower bound. This real number is called lower bound and f of x is said to be bounded below. Next we define greatest lower bound or infimum. Now we know the definition of lower bound, that is whenever f of x is greater than or equal to m, then we say that m is lower bound. So a real number small m is said to be greatest lower bound or infimum of the function f of x defined over closed interval a comma b if first point is this real number m is lower bound of f of x in closed interval a comma b. That means the value of f of x is greater than or equal to m for all x belongs to closed interval a comma b. Second point is whenever we know the lower bound, then the numbers less than this lower bound are also lower bounds of f of x. So this is the set of lower bounds. From this set we can easily find out the greatest lower bound, that is m. M is called greatest lower bound. So again the number which is greater than m, that is m plus epsilon, is not a lower bound because this is the greatest lower bound. Then the number greater than m plus epsilon is not a lower bound. If lower bound, it must satisfy f of x greater than or equal to m plus epsilon. But now I am telling m minus epsilon is not lower bound. That means it does not satisfy greater than or equal sign. That means f of x1 is less than, greater than is not possible, equal to is also not possible. So only one option is less than m plus epsilon. Here x1 is a point in closed interval a comma b. Then we say that m is greatest lower bound. One concept you can remember, whenever m is greatest lower bound, the numbers greater than m are not lower bounds. So once again, the second condition implies any real number greater than m cannot be a lower bound of f of x. The greatest lower bound of f of x is denoted by GLB. Next theorem, a function which is continuous in a closed interval attains its bounds. Proof, let f of x be a continuous function in closed interval a comma b. Given that a function which is continuous in a closed interval, so we can take f of x be a function which is continuous in closed interval a comma b. But we know one theorem, that is every continuous function which is defined in closed interval a comma b is bounded. So f of x is bounded in closed interval a comma b. Once again, given that a function which is continuous in a closed interval, so f of x is a function which is continuous in closed interval a comma b. But we know that every continuous function which is defined on closed interval is bounded. So f of x is bounded in closed interval a comma b. So bounded means it is both bounded above and bounded below. Whenever bounded above, you are going to get upper bound, that is m. Whenever it is bounded below, at that time you are going to get lower bound, that is small m. Whenever we know lower bound and upper bound, we can easily find least upper bound and greatest lower bound. So we can take m and small m be its supremum and infimum respectively over closed interval a comma b. That means capital M is supremum of f of x. Small m is infimum of f of x. We have to show that there exist points x1 and x2 belongs to closed interval a comma b. x1 and x2 are any 2 points of closed interval a comma b such that f of x1 equal to capital M, f of x2 equal to small m. Attains its bounds means this is the concept. F of x1 is capital M, f of x2 equal to small m. Since capital M is the supremum of f of x, capital M is supremum of f of x. That means supremum means least upper bound. So if m is least upper bound, then it is upper bound only. Upper bound also. Then it is upper bound also. Upper bound condition is f of x less than or equal to capital M. F of x is less than or equal to capital M. for all x belongs to closed interval a comma b. Now, if possible, let f of x is not equal to capital M for any x belongs to closed interval a comma b. So, here we have less than or equal. But here we are taking, if possible, f of x is not equal to m in closed interval a comma b. That means if x is any one of these points, the value of f at these points not equal to m. These points are all real numbers. When we know the function f of x, if f of x is x square plus 2x, if closed interval is 5 to 6, if you substitute this point, that is f of 5.3, you can get finite value. But this value not equal to capital M. This is our assumption. So we are considering the value of f at x not equal to m. So take this m to LHS side, then we are going to get m minus f of x not equal to 0. If m goes to LHS, here we are going to get 0. So, m minus f of x not equal to 0 in x belongs to closed interval a comma b. Once again, f of x is continuous in closed interval a comma b. This is given concept. M is a real number. So, m minus f of x is also continuous in closed interval a comma b. Real numbers are continuous functions. Continuous function minus continuous function is again continuous function. Therefore, m minus 1 by f of x is continuous function. Whenever m minus f of x is continuous, we can say that 1 by m minus f of x is continuous in closed interval a comma b. Y means 1 is a real number. This is continuous function. The denominator is already continuous function. Continuous function minus continuous function is continuous because of algebra of continuous functions. And also here the denominator is not equal to 0. Now this function is continuous in closed interval a comma b. But we know one theorem, that is every continuous function which is defined on closed interval is bounded. Therefore, this function, that is 1 by m minus f of x is bounded in closed interval a comma b. Bounded means it is both bounded above and bounded below. So, bounded above means we are going to get upper bound. Let k be an upper bound of this function in closed interval a comma b. Upper bound means it must satisfy function less than or equal to upper bound. Here the function is 1 by m minus f of x less than or equal to upper bound is k. That's why we are going to get this condition. Now interchange from this inequality, we are going to get 1 by k less than or equal to m minus f of x. I am interchanging this k and m minus f of x. Now I am rearranging this inequality. That means I am writing this as LHS greater than or equal to 1 by k for all x belongs to closed interval a comma b. Whenever we are going to change the places, less than or equal to become greater than or equal. Now I am keeping minus f of x here only. Plus m becomes minus m. Now multiply both sides with minus sign. Minus into minus is plus. Whenever we are going to multiply with negative, then greater than or equal becomes less than or equal. Minus m becomes positive m. Minus 1 by k becomes plus 1 by k becomes minus 1 by k. Observe, f of x is less than or equal to some real number. Then we can say that this is an upper bound of f of x. But this quantity is less than m. We already fixed capital M is supremum of f of x. From the definition of supremum, the real number less than m is not an upper bound. But what we are going to get here? The same quantity, that is the number which is less than m. Less than m is pakka. Why means here m is m minus something. So this quantity is less than m. But here what we are going to get? The number which is less than m is an upper bound of f of x. So this is the contradiction to the fact that m is the least upper bound of f of x. That means f of x value not equal to capital M for all x belongs to closed interval a comma b is not true. That means at any one point of this closed interval, take that one point as x1. This f of x1 value is m. Hence, there exists at least one point x equal to x1 belongs to closed interval a comma b such that f of x1 equal to capital M. Similarly, we can prove that there exists at least one value of x equal to x2 belongs to closed interval a comma b such that f of x2 equal to m. Therefore, the function f attains its bounds. Next, note. So, from this theorem, what we are going to observe? A function which is defined on a closed interval attains its bounds. Okay. Note, a function which is continuous and bounded on a open interval need not attain the bounds in that interval. For example, f of x equal to x, where x belongs to open interval 0, 1. This f of x is continuous because x is a polynomial. We know that every polynomial functions are continuous functions. And also, this f of x equal to x is bounded in open interval 0, 1. So, the infimum of f of x is 0, the supremum of f of x is 1. But this 0 and 1 does not belongs to this open interval 0, 1. Therefore, we can say that f of x value is not equal to f of x is equal to small m. This m is does not belongs to open interval 0, 1. In this situation m is 0 because in open interval the end points are not included. F of x equal to capital M. In this case capital M is 1 but 1 is also does not belongs to open interval 0, 1. Therefore, a function which is defined on open interval and also it is continuous and bounded, it need not attain its bounds.